Yeah. So, today we will discuss in this lecture the derivative of the function at a point as well as on the interval, and also the mean value theorem, differentiability, differentiable. Differentiability or derivative of the function, derivative of the function f x of real variables. Let f x be a real variate, let f be a real valued function defined over the interval say a b, over the closed interval say a b. Then the function f x is said to be differentiable at a point say x naught belonging to the interval a b, if the limit of this function f t minus f x naught divided by t minus x naught, limit t tends to x naught, if this limit exists and finite, of course, finite. In case infinite, we say if the limit is infinite derivative, then the differentiability we can also discuss the case of infinity later on only. Okay. So, let us say just exist, then it is denoted by f prime x naught, or we also say d over dx f x at a point x equal to x naught. That is also a notation to use the derivative at this point. So, now, here if the point is coinciding with a or b, then in that case we have a different concept. Now, when we say the limit of this exists, that is 1, if this limit exists means the existence of 1 means that both the limit, both left hand and right hand limit must exist at a point x naught which is in the open interval a b, and both are equal. Then we say the derivative of the function exists. At the corner point at x naught is equal to a, we consider only the right hand limit, that is we consider the limit t tends to x naught, say x naught is a. So, here t tends to a plus f of t minus f of a over t minus a. So, this is an interval a b. We will look only this side, the point which are approaching to a from the right hand side of a. So, this point t a plus. So, right hand limit of this, if it exists, then we say the derivative of the function at a point a. Similarly, the derivative at the point b, that is at the end points, this is the end point interval, means limit t tends to b minus f of t minus f of b divided by say t minus b. Okay, when b tends to t tends to b minus. So, if this limit is, we are taking the point, this is b, and we are approaching towards this side left of the b. All the points are taken in consideration which are left to b, and at this point we are taking the image of this when t tends to b minus. Then we say the function has a limit at the point b. So, if the function f is continuous, if the function f is continuous at every point of the closed interval a b, including at the end points, at end points, then we say the function f x is differentiable over the closed interval a b. Similarly, we say the function f, if f is differentiable, not it is differentiable at every point of the interval including endpoints, then similarly a function f is said to be differentiable over the open interval a b if it is differentiable at each point, at every point of the interval a b, like this. So, we can extend this definition to that side. Now, using this definition, one can easily show that if f x equal to 1, f x equal to x, the derivative will be 0. If f x equal to x, then the derivative of this function will be 1. In general, if f x is x to the power n, the derivative will be equal to n x n minus 1, which can be used, which can be proved directly with the help of this results. So, all the polynomials functions, all polynomials are differentiable functions, are differentiable function for each x belongs to R. Then polynomial p x, they are all differentiable function. Then trigonometric functions, like sin x, cosine x, tan x, these are all differentiable functions in the their domain, differentiable in their domains. Okay, like this. So, these are all examples which is just results which we know in the calculus, the differentiability of a various functions and formulas for it. So, we are not going in detail for that, but this. Now, interesting result is that every differentiable function will be a continuous function, that is. So, let f be defined on the closed interval a b, on the closed interval a b. If f is differentiable at a point say x belonging to the interval a b, then f is continuous, f is continuous at x. Okay. The proof is just simple. Okay. We want the continuity. So, let us take the point t which goes to x. Okay. So, take f of t minus f of x. This can be written as f of t minus f of x over t minus x into t minus x, where the t is different from x. So, obviously, this is well defined. Now, as limit t tends 2 goes to x. This gives the derivative f prime x by definition, and this part will give the 0. So, total will be 0. Therefore, limit of f t when t tends to x either from the left hand side or from the right hand side, if this limit exists, means it both will be equal. So, it will always give the derivative, and this will go to 0 whether we approach t from the t to x from the left or right. So, this will always be when t tends to x, the f t will be equal to f x. That is, the limit exists and equal to the value of the function at the point where the limit is required. This implies the function f is continuous at the point x. Okay. So, we have discussed this thing, the differentiability, and for the differentiability just we need only the functions to be well defined in this. And so, what is required now? If you look that this example shows, or this result shows, that continuity is a necessary condition for a function to be differentiable, because every differentiable function we are getting continuous. Okay. So, continuity comes automatically when the function is differentiable. So, it is a necessary condition for the functions to be differentiable, is it not? Then we say the converse of this. So, as a remark or note, the continuity of the function f x is necessary condition for a function f to be differentiable over the a b, or at any point, or at any point. Any point x belongs to a b. However, this condition, continuity of the function f is not a sufficient condition. For a function f to be differentiable. For example, if we look the function f x, which is equal to mod x, the function, the curve of this function is like this: x is 0, it is 0. When x is positive, then it y equal to x. When x is negative, y equal to minus a. So, we are getting again this one. So, this is the graph for mod x. Now, it is very smooth curve, it is a continuous curve. In fact, the function f x is continuous everywhere, say everywhere. I just take the interval for my convenience is 1 to 1, including at the point x equal to 0. The reason is because suppose I want to test at the point 0, what is the limit of the function f x when x approaches to 0 from positive side? The limit of this is nothing but what? F x is x. So, it is x, f x is s, and then limit x tends to 0 from positive side. This is the same as limit h tends to 0, 0 plus s, which is 0. And if you look the limit of this function f x when x tends to 0 from the negative side, then we say it is the limit x tends to 0, because all negative. So, it is x is minus, mod of x is minus x. Okay. So, this is minus x, x tends to 0, that is x equal to x minus h. So, we can write limit x minus h, a negative quantity, and then h tends to 0, x is 0. So, we get again it is 0, and the value of the function is equal to f 0. So, limit exists, limit of the function f x when x tends to 0 is 0, which is the same as f of 0. So, function is a continuous function at 0. So function f x, which is mod x, is continuous at x equal to 0, but it is not differentiable, but it is not differentiable at x equal to 0, because the reason is, if we find the limit of this function f x minus f 0 divided by x minus 0 as x tends to 0 from the positive side, what we get? Limit f x when a positive side is mod x, mod x means is simply x only. So, it is nothing but the x only, because it is positive, minus 0 and then divide by x, and x tends to 0 plus. So, this is 0 plus means when x is positive, mod x equal to x. So, limit comes out to be 1. When x tends to 0 minus the f x minus f 0 over x minus 0, this is the same as x minus. F x equal to mod x, when x is negative. So, it is minus x minus 0 divided by x when x tends to 0, but that comes out to be minus 1. So, what you are getting is the right hand limit comes out to be plus 1, left hand limit comes out to be minus 1. Therefore, limit of this function f x when x tends to 0 does not exist. Sorry, f x f minus f 0 over x minus 0, this does not exist. That is, the derivative of the function at a point 0 does not exist. So, function is not differentiable. It means the next continuity is no longer the sufficient condition. Okay? Just by looking the function is continuous, you cannot say the function must be a differentiable function. No, but it is a necessary. That is, if a function is not continuous, we cannot talk about the differentiability of the function. Function cannot be a differentiable if it is not at all continuous there. So, that is a very important result for that. Then, just like a limit case, we have proved that in case of the limit, if all continuity, if f and g are continuous, the addition of the two function is also continuous, subtraction is continuous, multiplication of the two continuous functions is continuous like this. So, similar results here also hold for differentiable functions. The results are in the form. Suppose f and g are defined. F and g are defined on the interval say a b, closed interval a b, and are differentiable at each point x belongs to a b. Then f plus g, f minus g, f g and f y g are differentiable at x, and the values of the derivative this x is the same as f prime x plus g prime x, b f g derivative at a point x is the derivative of the first function f x multiplied by the second. This is the product of the derivative of two functions. So, derivative of the first function multiplied by second plus the first function into the derivative of the second. Similarly, when we say the derivative of the ratio of the two differentiable function at a point x, x is the denominator g x into the derivative of the numerator f prime x minus numerator into the derivative of the denominator divided by the square of the denominator, provided the function g is not 0 in at any point where the differentiability is tested in this interval. Now, for the composite functions also the similar results hold as we have in case of continuity. Just like a function f is continuous at certain point and g is also continuous at the point f of p, where the image of point where the function is continuous, then f composition g is continuous at a. So, just like a continuity, the same result follows for differentiability. So, suppose f is continuous on the closed interval a b, and let f prime x exist at some point say x of a b belongs to a b. G is defined on an interval I which contains the range of f, and g is differentiable at the point f x, Okay. Now, if h of t equal to g of f t for t lying between this a to b, then g h is differentiable at x, and the derivative of this is equal to the derivative of g with respect to this f x, and then f with respect to x. Now, remember here I will just explain. Here we say note, when we say g dash of f x, it means we are differentiating this g with respect to f, and then f with respect to x, then f with respect to x. So, and f dash x is df over dx. So, when we are saying the h dash x, it means we want to differentiate this composite function g of f x. This composite function we want to differentiate with respect to x. So, since it is a composite function, g is a function of f. So, first we have to differentiate with respect to that composite function, and that composite function with respect to x. That will be the idea for it. Okay. So, that is the value for this. Okay. So, we get suppose for example, let me see just one thing. Suppose for example, I say the h function h of x equal to cosine of x square. Say suppose I take this, then f x is x square, g is cosine function. So, when you differentiate this h with respect to x, you will define cos with as if x square is t, a function of t, then cos of as a function t is the sine minus sine, derivative of cos is minus sine x square, and then x square will be differentiated with respect to x. So, that will give 2x. So, that is the composition. Okay. So, this is all. Now, let us see the proof of it, and 0 when x is equal to 0. Okay. Now, when x is not equal to 0, what you are getting is the function is defined in this fashion. Now, x square is continuous function, it is also differentiable function, sine is continuous and differentiable, so far x is not equal to 0. So, we can directly apply the formula, and when we take x is not equal to 0, when x is not equal to 0, you can directly apply the formula product of the two function, and product of the two function will give the derivative of the first 2x sin 1 by x, and then the second function x square, and the derivative of this is cos 1 by x into minus 1 by x square, because this is a composite function now. Derivative of sine as a function 1 by x is cos 1 by x, but 1 by x derivative is minus 1 by x square. So, it is a composite function. So, this holds when x is not equal to 0, that is the derivative of the function comes out to be 2x sin 1 by x minus cos of 1 by x for x which is different from 0. Okay. But when x is 0, what happens? The derivative of the function we have to compute it. Why? Because at the point x is 0, when you are looking for the derivative, then the value at this point apply the value which are different from x 0 is given by this form. So, find the derivative of this function at the 0 by using the definition, that is limit of this f x minus f 0 over x minus 0 x tends to 0. Okay. And that comes out to be what? F x is x square sin 1 by x minus 0 divided by x when x tends to 0. So, that is equal to basically limit of this x tends to 0 x sin 1 by x. Now, if we look that term x sin 1 by x is always be dominated by mod x, So, basically when you are taking the mod of this, then this is mod of this which is less than equal to mod of x limit x tends to 0, and this limit will always comes out to be 0. Okay. This limit comes out to be 0. Therefore, the limit of this exists and the derivative at the point 0 will be 0. Okay. But what about the equation? Let it be this equation 3, this is 4. The function is differentiable. So, conclusion is the function f x defined by say here star is differentiable throughout x belongs to R including x is 0, but the derivative of the function f x, if you look, the derivative is not continuous at x equal to 0. Why? Because when you take the derivative is involving cosine of 1 by x. So, when you take the limit as x tends to 0, the limit does not exist, because limit of the cos 1 by x as x tends to 0 does not exist, which is available in 3, because use 3. Okay. Then we are getting. So, when the function is differentiable, you cannot say that derived function remains continuous. It may not be continuous. If it is continuous, then there is a possibility of going further, is it not? But if it is not continuous, we cannot talk about the derivative. So, in this case, we cannot talk about the differentiability second derivative of the function at a point 0. Okay. If we look, the f x is similarly x sin 1 by x, we will see in a similar way the limit does not exist. Similarly, example 2, if we take the function f x, x sin 1 by x, x is not equal to 0 and 0, then function is continuous. F is continuous because at 0 and also for all x belongs to R. In fact, continuity follows, but not differentiable at x equal to 0. It is difference at rest of the point, rest it is differentiable, because when you take the derivative of x for x is different from 0, you can just apply the formula. First function x, derivative of this is cos 1 by x into minus 1 by x square, then plus sin 1 by x. So, the derivative will come out to be minus cosine 1 by x divided by 1 by x and then plus sin 1 by x when x is different from 0. But when you consider the derivative at a point 0, then as per the limit f x minus f 0 divided by x minus 0, x tends to 0. This comes out to be sin 1 by x minus 0 by x, x sin 1 by x minus 0, limit x tends to 0, which turns out to be limit of 1 by x as x tends to 0, which does not exist. So, this function is third continuous function, but is not differentiable at the point 0. It is differentiable at rest of the point, but not at the point 0. Okay? So, we can get